All right, good afternoon. We are pleased to welcome you to the Washington Labs Academy webinar series. We hope you find the next hour or so useful and informative. And now I'd like to introduce our presenter, starting with Greg Czumak. Greg Czumak is a senior TCB reviewer, a veteran of the wireless regulatory industry, serving for a dozen years at the Equipment Authorization Branch at the Federal Communications Commission. Greg has reviewed thousands of devices for compliance with the FCC, ICIT, Canada rules, and is on the board of directors of the Telecommunications Certification Body Council, also known as TCBC. Greg has given lectures, sermons, and presentations for a variety of audiences and continues to tackle complex device applications. So, without further ado, let's turn our attention to millimeter wave technologies and applications with Greg Czumak. Hi, Greg. It is all yours. Take it away.
Thanks, Kim. Wonderful to be here with you all once again. Very excited about this. Want to thank everybody who is attending as well for your participation and your interest. I wanted to mention that I'm going to be sharing the stage, so to speak, with a couple of other presenters today as well. They are Chris Harvey and Mike Marcus, and I will let them each give a brief introduction of themselves when they're ready to come on. But we're going to be all covering slightly different aspects regarding this particular topic. So I'll be going first, and we're going to be I'll be working basically in an introductory kind of capacity here as we begin to talk about millimeter wave technologies and applications. Um, as Kim noted, as Kim noted, I started my career out at the FCC right out of college, and this was back in the 1980s, quite some time ago. Doing equipment authorization. And I've been involved in that capacity one way or another ever since then, working for a number of different commercial test labs and telecommunication certification bodies. Currently working for American Certification Body and been there for the last 9 or 10 years. And also serving on the board of directors of the Telecommunication Body Council, the executive director of which is Chris Harvey, who will be our next presenter. So I'm going to be talking today a little bit about millimeter waves and the very fact that the whole sub-terahertz and terahertz realm has been becoming ever more exciting with the breakthroughs and technologies recently that have allowed more and more development and research to be performed in these areas here. Um, there have been many different types of wireless applications that are being developed with respect to the use of millimeter waves that are going to be used in enhancing infrastructure, expanding broadband services, and creating many new industries in the wireless arena. Wireless applications, including communication in the sub-terahertz frequency range, have been recognized as vital components in future 6G wireless networks. And this is one of the big things that's been pushing the interest in these very small waves, these high frequency types of operation. A lot of testing, infrastructure, and user technologies have been evolving as a result since this time. Just as a quick aside, I would note that the very fact that we're now dealing in hundreds of gigahertz is truly an amazing thing. When I was at University of Maryland in the mid 80s, I was lucky enough to have the opportunity to work for a couple of years at the plasma physics lab there on campus. The one professor whose research project I was working on was Dr. Granitstein. And as I recall, he actually held the patent for the first magnetron that was created in the United States and is used in every microwave oven pretty much everywhere in the world since then. We were working on a gyroclystron project back in 1986 that was operating at the ridiculously high cutting edge frequency of 5.8 gigahertz. So you can see how far we've gone in what 40 years. We're now dealing in hundreds of gigahertz and quickly approaching use in the terahertz frequency range. So quite an advancement over just a few decades there. Spurred by research at many leading universities, the growing understanding of millimeter wave propagation and potential interference mitigating strategies is rapidly progressing. Along with innovative signal processing, communication, and networking protocols, many new applications have been developed. Work is being done on the security of terahertz links as well. And in addition, their coexistence, the coexistence between active and passive users of the spectrum above 100 gigahertz. I know Mike will be speaking about this as well, but while there is a lot of open frequency, so to speak, above 100 gigahertz, the way that the rules have been written do not necessarily allow potential users to use as much of the spectrum as they might otherwise have imagined that they would have access to, which has been some cause of some concern amongst many in the industry. So the terahertz field has long been used for a wide variety of scientific applications, including radio astronomy, spectroscopy, fusion plasma diagnostics, and many more. The potential of these non-scientific applications has been understood for many years, but the technological limitations of the equipment has been what has been holding things back. Luckily, in the past decade, we have seen dramatic advances in transistor technology that's now enabling rapid progress in a variety of different applications, ranging from basic test and measurement to include ultra-wideband communications and also the use of terahertz radiometers in space, which is going to be used for the next generation of commercial weather forecasting. Extensive research and development for wireless devices above 95 gigahertz is currently underway. There's been a significant effort among academic, industry, and government leaders to really foster and develop new technologies, new wireless technologies and services that might be used in these bands. This includes efforts by the FCC, the Federal Communications Commission, in their support of 5G and 6G wireless services in the frequencies that are at the millimeter wave, sub-terahertz, and eventually into the terahertz bands themselves. Looking at this from a regulatory perspective, prior to March in 2019, the FCC service rules stopped at 95 gigahertz. But as of 2021, US allocations now extend up to 275 gigahertz, with the FCC claiming jurisdiction over the airwaves all the way up to 3 terahertz. Use of the technology above 95 gigahertz is governed in the United States by the FCC's docket or report and order 1821, which was released again in 1921. Now, ITE rules, the International Telecommunications Union rules, of which the United States, of course, is a part, they call for protection of primary passive spectrum, and this is particularly above 100 gigahertz, and this is made use of by primarily radio astronomy. There are some other uses as well, but they call for protection of primary passive spectrum by prohibiting quote unquote all emissions in certain bands. Now, there was a WRC 2000 call for studies to be performed regarding the feasibility of sharing in some of these bands. Unfortunately, not too many of these studies have taken place up until now, and so things are a little bit lagging behind in that area. And again, these are some of the topics that Mike will be covering during his talk as well. But if fundamental physics and engineering solutions offer foolproof ways to share these passive bands with terrestrial users, then these possibilities should indeed be explored. Worldwide, there's general uncertainty regarding service rules in the 95 to 275 gigahertz bands. There are no, for example, provisions for terahertz spectroscopy existing today, despite the fact that there are products that are being made and sold on the US market, both domestically and coming out of foreign companies. Global regulatory agencies, such as Japan's MIC, the Ministry of Internal Affairs and Communications, the CEPT, the Conference of European Postal and Telecommunications, the FCC, Canada's ISED, Innovation, Science and Economic Development, and England's Ofcom have all been adopting rulemakings that have created available spectrum above 100 gigahertz. I noted the RSS 295 of ISED was one of the most recent that was just released in the last couple of weeks, dealing with opening up bands and opening up allocations in these particular bands. So in March of 2019, FCC ET docket 1821 introduced 4 new unlicensed bands. And UK's Ofcom also followed suit. In the same decision, the FCC also created the Spectrum Horizons experimental radio licenses for, quote, experiments and demonstrations of equipment designed to operate exclusively on any frequency above 95 gigahertz, end quote. The FCC stated applicants for Spectrum Horizons licenses may request authorization on any frequency within the 95 gigahertz to 3 terahertz frequency range, subject to two very important restrictions. The first of which is this: each application must include a narrative statement describing in detail how its experiment could lead to the development of innovative devices and or services in the frequencies above 95 gigahertz, and describe as applicable their plans for how they're going to be marketing these devices. This statement must sufficiently explain the proposed new technology and potential new service, and incorporate as interference and I'm sorry, and incorporate an interference analysis that explains how the proposed equipment would not cause harmful interference to other services. And the citation from the rule is noted there. Spectrum Horizons license applicants that propose to use spectrum exclusively allocated for passive use or uses must provide an explanation why nearby bands with non-passive allocations are not appropriate or adequate for the experiment. In other words, why they have to use these particular passive bands to do what they want to do, and to also acknowledge that they intend to transition any potential long-term usage to a band with appropriate allocations. In other words, moving forward, if the FCC does make a decision to allocate certain specific bands for these things, then the equipment that has been authorized until then would have to migrate into those newly allocated bands. The report and order addresses two important uses and approaches, and this is something that really comes into play with regard to any type of transmitter that's being manufactured or I should say marketed and used here in the United States. These deal with either licensing procedures or unlicensed use. And again, every transmitter that's used here in the United States is going to fall into one of these two categories. Naturally, the licensed usage categories require, in addition to equipment authorization, a site license that is an application that for which they must apply and be approved by the FCC. Unlicensed use, on the other hand, deals with equipment created under Part 15 of the FCC rules. And once the equipment is authorized or certified under Part 15, then it may be used by anybody in any location without the need for any further licensing requirements. Now, for licensed use, the Commission refers to its Spectrum Horizons experimental radio licenses policy, which was developed in the report and order, which will consider applications for experimental use in the 95 gigahertz to 3 terahertz bands. In this action, the FCC states that they, quote, will not, by rule, preclude the use of any specific frequencies. By adopting this expansive approach to experimental licensing for these bands, we seek to foster an environment where innovators can develop new products. The FCC is hesitant to take any action that may stifle innovation. So certainly it would appear that while others in the federal government may not be so excited about opening up usage over 100 gigahertz due to their fears over protecting the numerous passive bands that exist in those frequency ranges, the FCC at least seems to be quite eager to back the creation of new technologies that will make use of these frequencies. Now, with respect to unlicensed operation, the following bands have been made available. This is all under Part 15 of the FCC rules: 116 to 123 gigahertz, 174.8 to 182 gigahertz, 185 to 190 gigahertz, and 244 to 246 gigahertz. Note that this totals a fairly impressive 21.2 gigahertz of spectrum, but these are still not the large continuous blocks of unlicensed spectrum for which many were hoping to obtain, thus enabling potentially even more and greater technologies and uses. A number of devices have subsequently obtained equipment authorization under Section 15.258 for unlicensed operation. This is going to be ending my introduction. I'm going to be handing this over to Chris Harvey after this, who's going to be going on and talking in detail about these devices that have obtained authorization already to this point under 15.258. So thank you all very much. And we'll be certainly have a time set aside for questions and discussion at the end. But at this point, I'll go ahead and pass this over to Chris Harvey.
Literally pass. Hey, good afternoon. Let me get my presentation ready. So my name is Chris Harvey. I am the Executive Director of the TCB Council. As Greg mentioned, Greg is the Chair of the Board of Directors, and I've been doing the TCB Council work for a little bit over 20 years now. Goodness. Time flies. We must be having fun. Here. And presentation mode. And okay. It didn't work. Yeah, to me. Something must have happened. And let the magic begin. There we go. I will share. And screen 2. Okay, thank you for your patience. So I'm going to kind of continue on from where Greg left off. But with that, I'm going to introduce a little bit about what the TCB Council is and who we are. Kind of a shameless plug. Have to do that to get more membership, right? So the TCB Council is an educational nonprofit organization. We are in the U.S. A tax 501c3 organization, and our purpose is for educating the community that needs information about the telecommunications certification bodies and the whole process for certification here in the U.S. and beyond. Our purpose is what we call sharing knowledge of regulatory compliance for tomorrow's wireless world. And I want to thank my wife for coming up with that a few years back. So we were created in 2003 as an organization to pick up the purposes of the FCC certification that were privatized a few years before that. We started out as just a little committee and then grew to an organization that's a couple thousand people large. We sponsor biannual workshops. We've been holding those in the Baltimore, Washington area almost exclusively just because we can get the FCC to show up in large numbers. We also sponsor conference calls monthly between the FCC and the TCB organizations because we are doing really the work of the FCC in issuing the grants of certification. We offer various online training sessions, including a basic training to get people acclimated into doing the type of work that the TCBs do. And we also help to gather information and dialogue between our community and the FCC as they make changes to their organizations. Right now, the TCB organizations themselves, the organizations that issue the certifications, we are 39 or maybe 38 in number all around the world. About half of them here in the US. The rest are kind of scattered around the world with countries that have MRA or MRAs between the US government and their governments. We also have 17 government organizations that are non-dues paying members of the TCB Council, and they are typically the regulatory bodies or the accrediting bodies around the world. We have what's also 165 companies that are associate members to the TCB Council. And with all of those companies that are members, there are roughly 1,800 plus people that are associated with the TCB Council membership. Yeah, there's my shameless plug. My email address is at the end if you are interested in becoming a member. Anyway, so Greg's already mentioned some of this, the regulatory requirements for millimeter wave. The FCC has adopted in the unlicensed rules, F15, Part 15 of the rules, Subpart C is section 15.258, and it's in those 4 bands that Greg had mentioned. And he also mentioned that Canada has just recently published their Canadian regulations and measurement requirements, known as RSS 295. And currently it is issue 1. So, and they have adopted the same 4 frequency bands. And that again was just in the last few weeks and maybe a little bit more than a month. So I went to the FCC's database where you can search for all kinds of information about devices that have been approved. And believe it or not, as of a couple days ago, there were only 12 applications that have been approved for operation in 15.258 for the millimeter wave, the above 100 gigahertz. All of them are contained within that first band. So there's nothing in the other 3 higher frequency bands. This is just a clip of the FCC's. If you go to the FCC's database for an equipment authorization search and just click on the parameters for include frequencies above 100 gigahertz, this is the list you'll come up with. So yeah, as I mentioned, there were only 12, all in the 116 to 123 gigahertz bands, and all of them seem to be for either radar or field disturbance type devices. And I didn't finish off a thought that I had there, but and the power levels that have been approved are all in accordance with the rule requirement, a limit of 20 watts peak EIRP, but the approvals have only been upwards of 111 milliwatts or lower of peak EIRP. And as of yet, there have been no approvals for the Canadian RSS 295. It's too quick. Even if people were submitting an application on the first day, Canada would not have yet approved them. But so I went onto the FCC's database and dug a little bit deeper and grabbed some screenshots of some of the devices that are being approved. And so you can take a look at them. They're typically very, very small, which I guess would be right for operating in 116 gigahertz. They typically are for sensor devices. So I didn't dig very deep, but I looked into what they are claiming their devices do. And there were devices for respirator and cardiac monitoring, presence detectors, and I think that was the presence of humans, so kind of a field disturbance type of device, radar level sensors for levels of liquids, again, just straight up field disturbance sensors. One interesting one, if you see the one down near the bottom center, is a muzzle velocity sensor. Actually, you clip it onto your rifle and it measures the velocity of the bullet that's coming out of the muzzle. Wow. And then a short range radar devices. So radars, sensors, field disturbance sensors, and that is so far of the 12 devices that have been approved. One of them was approved long enough that there was actually a change, what's known as a permissive change application, and they added some additional functionality and hosts. Continuing with my shameless plugs, I mentioned the biannual workshops that we do. Our next one is about 3 months away from now in October 14 to 17. The first day will be a RF exposure day. So just SAR, MPE, what's happening up in the much higher frequencies. We're not yet doing the RF exposure of the millimeter wave stuff, but it's up there. And there is lots of discussion about that going on. So that first day is just for RF exposure, but the October 15 to 17 is what we call our regular 3-day workshop program, where we have regulators from Canada, from US FCC, and from other regulators around the world, and laboratory and technology experts that come in and give information about what's up and coming, problems that people are having, really just provide an education about what's going on in our community. And you can go to the www.tcbcouncil.org to get additional information. So I think we're going to wait until the very end to do questions. So if you do have questions, please save them. And thank you very much. I'm going to go ahead and pass over to Michael Marcus. So in fact, let me get the session started. We'll stop that share. We'll switch over. Yeah, I'll pass you this. And this is Greg's. And my mouse never changed title. For some reason, my mouse is disappearing. Okay. Thank you. And use the arrows to go down. Able to use the arrows. Yep. Great. Okay. Hey, my name is Mike Marcus. I'm overeducated, and I work with a bunch of overeducated people, both as a consultant and in academia. Oh, have I shared? Oh, yes, I have. Yep. Okay. Okay. So these are some of the overeducated people I share with. I work with, and we're Northeastern University may not be the biggest name in electrical engineering, but they are certainly very, very active in above 100 gigahertz. So that's why I've associated with them at this stage in my life. This is okay. It's not showing up. Let me. Okay. I'm going to talk about. Yeah. Let's see what's going on. Technical difficulties. Do 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 do. Okay, let's see if
Okay.
Yes, thank you.
Okay. How do I go back? How do I go back here? Okay, here we go. There we go. Okay, so anyway, this is where I work part-time at Northeastern University in Boston. I physically live in Washington, but this is a distinguished team that I'm involved in and looking above 100 gigahertz. But I thought I'd focus today on things more that TCBs would be interested in and help guys. Let's go right here. See if that'll do it. Okay. How do I? Okay. That's what I looked like in 1985. Do I look any different today, gang, than that?
Why no?
No. Okay. That was my career at FCC spread went from 1979 to 2004, but the red dots there are decisions that I both proposed and managed the rulemaking of. So starting in 1985 is the ISM band decision, which brought forth Wi-Fi and Bluetooth. And then in 1994, I was responsible for the policies in 59 to 64 gigahertz, which much to my amazement has now become 57 to 71 gigahertz. And while it isn't worldwide, it's sort of close to worldwide. And before I left in 2005, we got out the door another crazy idea of mine of the 71, 81 gigahertz bands, the so-called E bands, and the 92 band. The 78 bands have been very successful and have been implemented in many countries around the world. The 90 gigahertz band, not so much. So sometimes people listen to me and it has an impact. And I've been for the past 5 or 10 years, I've been very interested in above 100 gigahertz. Let me talk a general thing about having worked inside spectrum regulation. When you guys look at regulations, think they came down from Mount Sinai. They're not. They're made in a sausage factory by sausage makers like Greg and me. And here are some of the issues that really happen. Let's take the vertical axis. People worry about what industry thinks the regulator wants, and on the other hand, what the regulator thinks industry wants. And believe it or not, well, neither side understands each other well. And this is a problem that people make decisions assuming they know what the other guy wants, and they may not be making the right decision. And on the bottom side, you have the other practical problem is what is really needed to solve the EMC problem at hand. But on the other hand is what is really affordable with today's technology. So when you're writing a technical standard, these are the things that really are involved in the sausage factory and which result in decisions that are less optimal. So you may remember, those of you who are baby boomers or watch baby boomer movies may remember the great scene from The Graduate. Just one word,
plastics. So if you remember nothing else of what I say today, please remember the this one, antennas. As we get into SHF is 3 gigahertz and above, and EHF is 30 gigahertz and above, but they have things in common. The wavelengths are getting smaller. Too many people think antennas are what you find in catalogs, like that catalog is shown there. Those are antennas, but they're not all the antennas that can be built. And unfortunately, both industry and the FCC don't seem to understand that the world of antennas is much greater than what you find in those catalogs there. And the solutions for many spectrum problems is greater than that. And it is possible that people in the equipment authorization business and the regulators should start being concerned more about antenna issues. Uh, and okay, an example is total regulated power. Many of you, I suspect, are familiar with this concept. It is a convenient measure. It is a convenient number to put in both rules, such as FCC rules, and to if you're issuing licenses and have a box on the license that says maximum power, it's convenient to have a number to plug in there. And in some of the antennas that are commercially available today, specifically MIMO antennas, it's not obvious what that number should be. So many people have grasped the thing which is on the right, total radiated power, because it's easy to measure. The number you get from that measurement scales with power. It has something to do with power. And there is a FCC and the ITU are creating TRP regulations, and industry is busy measuring it because you've been told to measure it. But there's only one little problem. TRP does not have a general correlation with the interference that a transmitter causes. For a family of antennas, it may. For instance, for the MIMO antennas that are produced today by Ericsson and Nokia, TRP may really scale with the interference potential, but that is not a general truth for MIMO antennas or antennas in general. And this is an example of misunderstandings between industry and the regulators that while we don't have an alternative TRP, I think we should do that. We have to recognize the problems of that. Active passing sharing is a growing issue. And here's an example of looking at different regions of the spectrum, VHF, UHF, SHF, and EHF. Again, SHF begins at 3 gigahertz, EHF begins at 30 gigahertz. Passive bands have had little impact on spectrum policy in general, at least during the period I worked at FCC. I barely ever remember passive bands ever coming up. And as I like to joke, whoever missed TV channel 37? Indeed, what negligible fraction of the people in the United States even know that there is no TV channel 37? I suspect even of card-carrying IEEE members, hardly anyone knows that exists. Passive spectrum is just an exception to the rule of a quirky use of spectrum. But look what happens when you go from SHF up to EHF. You suddenly have 14 passive bands, not just 14 passive bands, 14 bands protected by radio regulation 5.340 that says all emitters are prohibited, period. Notice VHF and UHF and SHF, you only have 4, and in VHF, you only have 1. Now look at the right. The fraction that those bands take within that decade, and I frankly, if you want to compare hertz to hertz, you shouldn't compare hertz in the AM broadcast band to hertz at C band. You really have the only way to compare hertz for count hertzes and compare them is within a narrow range of 1 decade. So that's why I prefer to do it this way. In EHF, 14% of 17% of the spectrum not only is passive, but it's protected by 5.340. All emissions are prohibited. That's a lot of spectrum, but the worst problem is really the left, because those 14 bands chop up the spectrum between 30 and 300 into little pieces. And as Greg mentioned, you can't get big contiguous spectrum, bands of spectrum. And why in the world do you want to go above 100 gigahertz? If you're an amateur radio operator, you might want to go up there because you say, well, I was the first one to use 121 gigahertz. But in the real world, people don't want to make products just to say I'm at a higher frequency. But yeah, you want to make products for some new improved functionality. And this is the general problem. And those of us who deal with spectrum policy up there worry about that. Um, Talk about a lower frequency per minute. If you read the more general spectrum policy discussions, there was a big problem in the past couple of years over 24 gigahertz 5G band coexistence, not with someone sharing the same band, but with a adjacent band, their allocations table shown on the right, that's 250 megahertz away. And the passive satellite community, passive satellites, by the way, aren't just for academic uses. These passive satellites, in this case, are used for weather forecasting. So, in many people's eyes, correctly, it's viewed as a safety of life issue. There was concern about out of band emissions from the 24 gigahertz 5G band, the bottom band on that table, to the passive band, which is 250 megahertz below it. You can't, if you have these arguments over 250 megahertz separation, sharing the same band is clearly impossible. And so at WRC 19, resolution 750 was adopted, and its deliberations going on at FCC now in docket 21-186 on 5G TR limits on out of band emissions with the denominator in TRP. And if you think what I just told you a minute ago, TRP is easy to measure. What it has to do with interference potential, at least in general, is really, really confusing. But that's the way things are. Now, it is easy to forget that when frequencies increase, assumptions change. And my favorite example is the Yagi antenna was invented in part by Professor Yagi in the early 1920s. And Professor Yagi, being a loyal Japanese citizen, invited the Japanese military to look at his prototype directional antenna when the frequencies were 5 megahertz. And the 5 megahertz, you may recall, a 60-meter wavelength. Those antennas were pretty big. And the Japanese military quickly said, thank you, Professor Yagi. This has no practical use. Okay? And then suddenly in 1942, the Japanese captured a 400 megahertz British radar in Hong Kong and realized they were wrong. But basically, they had not developed radar because they didn't know directional antennas were possible, because they missed the boat that when frequencies went from 5 megahertz to 400 megahertz, the physics changed. Unfortunately, regulators are doing some of the same thing now. As frequencies get higher, wavelengths get smaller, and antennas can do functions that they can't do at the other frequencies. So if this seems difficult for you to imagine, to think about, I can only imagine. Say frequencies increase, lambda decreases. Antenna functionality basically scales with how big an antenna is as a multiple of lambda. 1934, FCC started going, actually its predecessor in 27. The only directional arrays were AM, the only directional antennas were AM directional arrays, which were considered very high tech in 1934. Clearly not generally applicable, and they really weren't that directional. Now that's the famous allocation table. In the bottom two rows, basically 30 gigahertz, 300 gigahertz, wavelengths are small enough that we can do a lot more with the antennas than we could do in 1934. This paper, by the way, is based mainly on this 26-page article in Proceedings of the IEEE last year, which I would recommend. And on passive spectrum, the history has been only in the 1980s did ITU start using the phrase "all emissions are prohibited in the passive bands." And first, it started with only a few bands, and so suddenly it's uh, how do I go backwards?
Should work on the arrows, but
Okay, but the number of passive bands protected by that phrase has been increasing, increasing, increasing. And I noticed that none of these bands have ever disappeared. They just keep getting at it. But that's uh, okay. I'm going to have someone else do this for me. Okay. 100 gigahertz and above is really very different than things most of us are used to. Maxwell's equations still apply. I will admit Maxwell's equations still apply, but propagation is very unusual due to a mixture of atmospheric absorption, and it varies in a complex way with both frequency and altitude. You literally can get path losses greater than 1,000 dB in some cases. Think about this. Have you ever seen any number denominated in dB greater than 500? 1,000 dB, and actually it turns out it can be greater than 1,000 dB, is really a really big. This is a strange part of the world. I show some pieces of hardware at the right. This is above 100 gigahertz hardware. This is not necessarily how you build equipment for production, but this is how these are devices which you use for prototyping equipment. It is really weird stuff, and a lot of the things you're used to with VHF and UHF, you really have to recalibrate your thinking. Antenna approaches which make no sense at lower bands. For example, literal lenses are possible here, which don't exist at other frequencies. Do Maxwell's equations apply? Yes. Okay. All finite antennas have side lobes, but a small wavelength allows more complex antennas. And the green dots remind you of what the wavelengths are above 100 gigahertz there. And you have to start thinking this way. Another reason you want to go up there is to get high capacity. And the lower right chart comes from an Ericsson publication that talks about what's used for backhaul today. And green is the fiber, but microwave is the upper part, which is blue. Fiber and microwave are sort of comparable in their market shares today for backhaul. And Ericsson indeed predicts it for it going into 2030 that great. Uh, the problem is that if 6G is successful, or even if it isn't successful, if the internet keeps growing, you need links of up to a terabit per second, and the current radio allocations can't support that type of rates. So one thing it's needed for is 6G backhaul, front haul, or for terrestrial internet networks where not to replace fiber, don't sell your Corning fiber stock, but you can't build networks 100% with fiber. And if you could, you couldn't repair them quickly if they broke. Because when there's disaster, you can't always repair a fiber network quickly, particularly in earthquake situations where the ground splits. Now, in Fukushima earthquake, it turns out they did not have this problem, but the Fukushima earthquake was 100 kilometers offshore. The earthquakes we have in California are not offshore; they take place on land in California. Hopefully, land doesn't have much fiber in it. The other issue is the amount of passive bands. This is the 100 to 122 gigahertz, but look at how many passive bands you have in there. I strongly recommend this book, which is free over the internet. The PDF is free, which helps you explain more about this. A minor disagreement with my former colleague, Greg. Radio astronomy is theoretically an issue. In reality, it isn't. And the reason it's not really an issue is radio telescopes of this frequency are very expensive. The atmosphere is a major limit to them, and it's crazy to build a radio telescope at these frequencies unless you put it on a high arid mountaintop. So in the world, most of the radio telescopes in this frequency are actually in northern Chile. In all of Europe, there are only two. There are several in the United States. The only one that has an interference threat from civilization is 100 miles west of Tucson. So there is a problem in the western suburbs of Tucson, but that's the only place in the world where there's a radio telescope that would interact with any semblance of civilization. That's a subtle point, but uh, it's the passive satellites. But the passive satellites do marvelous things. Uh, why is this help? Still causing troubles. Okay, no, that's going backwards. Whose computer is it? Whose computer is this?
It's mine.
Could you give me the next slide, please? Okay. Okay. Here we get the derivative advantage. Move on. Okay. Propagation is different. This rate. No. You hit the button. The propagation is different. This shows molecular absorption, which is a function of frequency. Turns out it's also a function of altitude and humidity. Next slide. Now you can get frustrated. I don't need the blood pressure. Okay. Here is the real quirky things from an article I published a year or so ago. Left shows you from the path loss for a 700-kilometer path to a satellite based on elevation angle, and look at the left end of that. That's where you get numbers as high as 5,000 for path loss. So the interference from a terrestrial user to a satellite depends on the elevation angle of the satellite from where you are, and for low elevation angles, that is, if when the satellite just rises over the horizon, the path loss at some frequencies is huge. At other frequencies, not so much. And on the right shows how another quirk of the propagation. This shows for 60 degrees satellite path. If you took a measurement probe and moved up the path from a transmitter all the way up to orbit, clearly it's not something you'd physically do, the path loss becomes S-shaped, because in the first segment, it's dominated by free space. In the next segment, it's dominated by absorption, but then you get high enough up in the atmosphere, there are no more molecules left, and it suddenly reverts back to free space. You've got to address these problems differently, and antennas will become important next. Okay, indeed, here's an example of a quirky antenna that's used in this frequency. Shows you what the antenna patterns could be. These antennas do not have good side lobe suppression, but the reason they don't have good side lobe suppression is FCC never said they needed them. It doesn't mean you can't build one with side lobe suppression. I'm going to have to stop in a minute. Yes, I know. Okay. And if you think you understand how propagation works, Maxwell's equations work. You would think in Maxwell's equations, radio waves always go straight. This is cutting edge engineering from an article published a few months ago on a phrase you've probably never heard, airy beams. That's not fairy beams, it's airy beams. This is a way you can create an electromagnetic propagation which literally curves. It doesn't go straight. These are solutions to Maxwell's equations. This is not the solutions we normally see, but it is a solution. This is very, very different. And we all have to work together to do this. But one more, and then that's it. Okay, good. Antennas may well become a big issue in this thing. Should all test labs build a multi-million-dollar antenna test range? Probably not. There probably is enough market demand for that. But the industry might want to think about how do we come up with a test range that can measure antenna characteristics at these frequencies, and maybe somehow a shared facility. Not every. How many test labs are there? 100 odd. You're not going to build 100 odd multi-million-dollar test ranges. So thank you for this opportunity.
All right, you can be
good. All right. Well, thank you all. I would just like to go ahead and thank Greg, Chris, and Mike for such a very informative webinar. Let's go ahead and check to see if we have any questions. And just in case you didn't know, if you have any questions, please go ahead and submit them in the chat box for me, and I'll be happy to read them.
Have a live question.
Yeah, look at Mike's last slide. So you're saying that propagation is actually curved.
So you could, there are bizarre antennas you can build that create curve feeds. If you build a conventional antenna, it doesn't curve.
Right.
But there are bizarre antennas you can build. I mean, physically they're like MIMO antennas, they're multi-element. But depending on how you excite the different elements in the MIMO antenna, you can do some weird things, and including beams of curve. Yep.
So effectively going around a corner.
Yes.
Thank you.
Interesting.
Okay, I do have a question from those who are online. The question was, the attempts to use millimeter wave bands in cellular networks have largely failed. The latest example is that South Korea closed down all its networks. Any comments to that?
You're talking. The issue here is really mobile links, uh, and the millimeter wave mobile links have huge capacities. But the question is, does anyone need huge capacity for individual use of mobile downlinks? What I've been focusing here is um, basically not the mobile links, but the backhaul that supports them. And as total use grows, the backhaul requirement keeps growing even further. So I must admit, it isn't obvious you need frequencies of 100 gigahertz or even 20 gigahertz for mobile links, but it is becoming clearer that with more and more data that's flowing around, point-to-point links have a different demand than mobile links do, although they're related. And the need for the growing amount of data in society is going to meet more need for data for information to get from point A to point B, and that's basically fixed service as opposed to mobile links.
Okay, thank you. Last question I actually see is from Brett, and he said, can you drop that link? I did see the question come in when you were speaking, Mike. I'm not sure what link he's referring to. And Brett, if you want to elaborate more, so maybe Mike can drop the link, that would be helpful. And while we wait on Brett to maybe elaborate what link he's referring to, I will just go ahead and say, if we didn't get to your question, or if you have additional questions, you can always email us here, and I'll put in the chat box as well at questions@wll.com. That way I can take the question and forward it to one of our panelists and get a response for you. And again, while we wait on Brett to maybe elaborate on the link, I would just go ahead and also like to say our next upcoming webinar will be on Mills Standard 810 DO160. That is next month on August 15th. So if you haven't already done so, please make sure you visit our website to subscribe to our Washington Labs Academy to receive updates. This is easily done by visiting www.wll.com. You'll click the training tab in the upper right corner and fill it in your information where you see sign up for updates. And Brett did say it was the link. The link was on one of the first few slides before the IEEE paper. So I'm not sure who presentation that exactly was, but it was a link he's looking for.
Was it near the beginning?
Yeah, first you said, yeah.
Yeah, the first few slides. Now I'm thinking of the presentation itself. Maybe not Mike then.
Okay,
That was it, I bet. Maybe that one there.
Yeah. Is that the one you were looking for?
There's nothing showing on the screen at the moment.
Oh, I stopped sharing. That's why. Yeah. Is this the slide?
Is this it, Brett?
Is
He said yes.
Okay, I will drop that into the chat. See if I can. Okay, yeah, I will. I have to stop sharing in order to clip it, but I will drop it right into the chat.
Okay. And I won't close it so that way Brett and whoever else might need it can grab it. But I would like to go ahead and just say on behalf of the Washington Labs Academy, we would like to thank you all for attending. I will now end the event, but I'll keep it open so we can capture that link. But please enjoy the rest of your day and most importantly, be safe.
Okay,
Thank you.
the link is there.
Yep, it is. I do see it. Thank you so much. And thanks again
All right,
to our
thank you,
panelists.
everybody.
Very interesting. Good job.